Okay, so we continue. Okay, saglit. Mhm. Okay, so figure shows the block diagram of a centralized multi-point data communication circuit using several paths data communication links to interconnect three endpoints. Okay, so the circuit is arranged in a bus topology with a central control provided by a mainframe computer at the endpoint A. So, endpoint A yung sa mainframe. So, host is sometimes called the primary station. So, endpoints B and C are called secondary station. So, the primary station is responsible for establishing and maintaining the data link and for ensuring an orderly flow of data between itself and each of secondary stations. So data flow is controlled by an application program stored in the mainframe computer at the primary station. So the primary station, there are mainframe computer, a front-end processor, which is a GTE, and a data modem. At the secondary station, there is a modem, a line control unit, and a cluster of terminal devices. So line control unit at secondary station is referred to as cluster controller as it controls the flow of data flow between several terminal devices and the data communication channel. Then line control units at secondary station are called station controllers as they control flow to the uh, data flow to and from all data communication equipment located at the station. Wait lang. Sorry. Mali ito eh. Dapat primary station doon. Okay, so the first class, yung cluster controller is in the primary station. So, nga pala, na-correct ko na to dati. Okay, so line control unit at primary station is referred to as cluster controller. Then, line control units at the secondary is called station controllers, no? So, or stacos. For simplicity, Figure 10 only shows one data circuit served by mainframe computer at the primary station. However, there can be dozens of different circuits served by one mainframe computer. So therefore, the primary station line control unit must have enhanced capabilities for storing, processing, and retransmitting data it receives from all secondary stations on all the circuit it serves. So the primary station stores software or database management for all of the circuit it serves. So obviously, the duties performed by the front-end processor at the primary station are more involved than the duties performed by the line control units at the secondary station. So there are both line control units, but dun kasi sa primary station, tawag dito, pinangalanan siya as front-end processor. But they are both line control units. Mas advanced lang yung front-end processor, no? So, FEP, or front-end processor, directs data traffic to and from many different circuits, which could all have different parameters such as different bit rates, different character codes, data formats, protocols, and so on. So, the LCU at the secondary station directs traffic between one data communication link and a relatively few terminal devices which all transmit and receive data at the same speed and use the same data link protocol character code, data format, and so on. So next, we have line control unit. As previously stated, line control unit is a DTE, and DTEs have several important functions. So the primary station, the LCU, is often called front-end processor because it processes information and serves as an interface between the host and all the data communication circuit it serves. Mas advanced siya. Kasi kaya niyang umintindi kahit iba't iba kayo ng protocol, yung kagaya ng kanina protocol, character codes, bit rates, mga ganyan, no? So each circuit served is connected to a different port on the FEP. Then FEP directs the flow of the input and output data between data communication circuits and their respective application programs. So the data interface between the mainframe computer and the FEP transfers data in parallel at relatively high bit rates. However, the data transfer between modem and the FEP are accomplished in a serial at a much lower bit rate. So the FEP at the primary station and the LCU at the secondary station perform parallel to serial or serial to parallel conversion. So sila yung bahala dun, class, no? Yung pagpapunta na sa kuhan sa station, so we have parallel, pero pagpapunta sa modem, we have serial. Okay? Kaya nga meron tayong serial interface dito, class. Okay, mga ganyan. Okay, kasi serial yung gamit dyan. Okay, so they also house the circuitry that performs error detection and correction. In addition, data link control characters are inserted and detected in the FEP and LCUs. Within the FEP and LCUs, a single special purpose integrated circuit performs many of the fundamental data communication functions. So this integrated circuit is called Universal Asynchronous Receiver Transmitter, or UART, if it is designed for asynchronous data transmission. So a universal synchronous receiver transmitter, or USRT, if it is designed for synchronous data transmission. And a universal synchronous asynchronous receiver transmitter, or USART, if it is designed for either asynchronous or synchronous data transmission. So all three types of circuits specify general purpose integrated circuit chips located in an LCU or FEP that allows DTE to interface with DCEs. So in modern day integrated circuits, UARTs and USARTs are often combined into a single USART chip that is probably more popular today simply because it can be adapted to either asynchronous or synchronous data transmission. So yun ang kagandahan sa USART, no? So USARTs are available in 24 to 64 pin dual line packages, or DIPs. UARTs and UARTs, USRTs, and USARTs are devices that operate external to the central processing unit in a DTE that allow the DTE to communicate serially with the other data communication equipment such as DCEs. So they are also essential data communication components in terminals, workstation, PCs, and many other types of serial data communication devices. In most modern computers, users are normally included to the motherboard and connected directly to the serial port. Then UARTs, USRTs, and USARTs designed to interface specific microprocessors often have unique manufacturer-specific names. For example, Motorola manufactures a special purpose UART chip it calls an Asynchronous Communication Interface Adapter, so ACIA. So these are the functions of UART. So we have parallel serial data conversion in the transmitter and serial to parallel data conversion in the receiver. Number two, error detection by inserting parity bits in the transmitter and checking parity bits in the receiver. Then insert start and stop bits in transmitter and detect and remove start and stop bits in the receiver. So dito na yung parallel to serial conversion, error detection, and yung start and stop, inserting and remove, inserting start and stop bits, no? Number four, formatting data in the transmitter and receiver. So combining items through 1 to 3 in a meaningful sequence, no? Number five, provide transmit and receive status information to the CPU. Pwede na ba mag-transmit? O kailangan ko ba mag-receive? Mga ganyan, no? Voltage level conversions between the DTE and the serial interface and vice versa. And last, provide means of achieving bit and character synchronization. Malamang using start and stop bits yan. So, terminal transmit and receive functions can be performed by UART simultaneously because the transmitter and receiver have separate control signals and clock signals and share a bidirectional data bus, which allow them to operate virtually independently of one another. So in addition, the input and output data are double buffered, which allow for continuous data transmission and reception. So figure shows a simplified block diagram of line control unit showing the relationship between UART and the CPU that controls the operation of UART. Okay, so the CPU coordinates data transfer between line control unit and the modem. So CPU is responsible for performing UART's control register, reading the UART status register, transferring data, parallel data to and from the UART, transmit and receive buffer registers, providing clocking information to the UART, and facilitating the transfer of serial data between the UART and the modem. UART can be divided into two functional sections, the transmitter and receiver. So figure shows a simplified block diagram of UART transmitter. So transmitter muna tayo class, no? So we have the control register, transmit buffer register, okay? Then we have adding of parity bits, okay? Then so on, no? Okay, before transferring data in either direction, an 8-bit control word must be programmed into UART control register to specify the nature of data. So the control word specify the number of data bits per character, where a parity bit is included, and with each character, and if so, whether it is odd or even parity, the number of stop bits inserted at the end of each character, and the received clock frequency relative to the transmit clock frequency. So essentially, the start bit is only the UART that is not optional or programmable, as it is always one start bit. So hindi niyo na kailangang i-mention or ilagay pa sa control register yun kasi ang start bit naman talaga 0 siya, saka isa lang talaga siya, no? So table shows the control register coding format for typical UART. Then this is the control word register, no? So we have 8 digits of control word register. So I specified in table 6, the parity bit is optional and use can be either odd or even. So to select parity, NPB is cleared, and to exclude parity bit, NPB is set or logic 1. Add parity is selected by clearing POE, and even parity is selected by setting POE. O gawin natin logic 1. Ano tayo? So number of stop bits established by with the NSB1 and NSB2 bits and can be 1, 1/2, or 2. The character length is determined by NDB1, NDB2, and can be 5, 6, 7, or 8 bits long. So the 8 data bits and 2 stop bits or 1 start bit, 7 data bits, 1 parity bit, and 2 stop bits. So using a 22-bit character format with ASCII encoding is sometimes called full ASCII. For example, we have this, no? Or mag-example na lang tayo. So, sabihin natin ganito. Okay, yung control word register natin, sabihin natin ganito siya. Okay? Example, this is the control word register. Yan yung nailagay na input sa control register natin, no? So, ibig sabihin, ito yung nature ng natin, ng data. So, ito yung ano niya, yung gagawin dun sa data. So, first, B76 kasi bit 0 to, tapos bit 7 to, di ba? Okay. 7, 6, 5, 4, 3, 2, 1, 0. Okay. So, D7 and 6, D6 is equal to 1, 1. Ito yun. Okay. So, kung 1, 1, big sabihin, we have 2 stop bits. Okay, next, D5 and D4. Okay. So, D5 and 4. Okay. So, yung D5, isa-isa lang pala to. The D5 indicates if there is parity or not. No? Since 0 siya, ibig sabihin, with parity siya. Then D4 indicates if it is parity, if its parity is odd or even. So, since this is 0, D4, okay, so, ibig sabihin, we use a parity. Okay? Kita ba? Okay, next. Then we have D3, D2. So, D3, D2 is 1, 1. So, big sabihin, yung character natin is 8 bits. We have an 8-bit character. Then, next, we have D1 and D0 is equal to 1, 0. So, ibig sabihin, receive clock natin, RCP, receive clock pulse, is equal to 16 times. Okay, 16 times yung RCP natin. Okay, so parang sabihin natin dun sa dun sa receiver indicating that the received clock pulse is 16 times. Okay? Okay, so we have this. Okay, first, we have transmit buffer empty. Transmitter muna tayo, no? Okay, so first, yung mga natin, yung mga terms natin. So we have TBMT, transmit buffer empty. Yung empty class, yung di ba TBMT? Tama naman. Parang mali yung kanya, yung meaning ng acronym. So empty means empty. Ito yun. Kakaiba, no? Yung empty na sinasabi, ito na yun. Okay, transmit buffer empty. So means that transmit shift register has completed transmission of data character. So, ito yung mga errors naman. Receive parity error. Set when a receive character has a parity error in it. RFE, receive framing error. Set when the character is received without any or with an improper number of stop bits. ROR naman, receive overrun. Set when a character in a receive buffer register is written over by another receive character because the CPU failed to receive an active condition on REA before the next character was received from the receive shift register. Then we have RDA. RDA, receive data available. A data character has been received and loaded into the receive data register. So, punta muna tayo ng UART transmitter. So the operation of a typical UART transmitter shown in the figure is quite logical. However, the UART can send or receive data. The UART control register must be loaded with the desired mode instruction word. So this is accomplished by the CPU in the DTE, which applies the mode instruction word to the control word bus and then activates the control register stroke. Okay, so ganito tayo class, no? Design natin. So we have the CPU and UART transmitter. So ano ba yung pwede mangyari dito? Okay. So figure shows the signaling sequence that occurs between CPU and UART transmitter. So the receipt of an active status word enable. Okay. So tatanungin nung magsisend yung central processing unit natin ng status word enable. Okay. So, sana tayo? On the receipt of an active status word enable signal, the UART sends the transmit buffer empty signal from the status word register to the CPU to indicate that the transmit buffer register is empty and the UART is ready to receive more data. So, anong status mo ngayon? Sabi niya doon sa UART. Sabi naman ng UART, transmit buffer empty. Walang laman yung transmit buffer ko. Okay, ngayon, ang gagawin ng Central Processing Unit, yung number 3. Ibibigay niya na yung parallel data. Okay? So when the CPU senses an active condition on TPMT, it applies a parallel data to the transmit data lines. So we have T7 through T0 and strobes them into the transmit buffer register with an active signal on the transmit data strobe signal. Okay? So, ilalagay niya yun. Once na sinabi na nung or nag-send ng transmit data strobe yung central processing unit. Okay, so the contents of the transmit buffer register are transferred to the transmit shift register when the transmit end of character signal goes active. Okay, so the TEOC signal is internal to the UART and simply tells the transmit buffer register when the transmit shift register is empty and available to receive data. So the data pass through the steering logic circuit where it picks up the appropriate start and stop and parity bits. After data have been loaded into transmit shift register, they are serially outputted on the transmit serial output. So lalabas na dito sa TSO. Pin at the bit rate equal to the transmit clock frequency or TCP. While the data in the transmit shift register is serially clocked out of the UART, the CPU applies the next character to the input of the transmit buffer register. So, process repeats until the CPU has transferred all the data. Nakikita natin dito yun. Ayun. So, bibigay mo na yung control word register, di ba? Para alam nung transmit, anong UART natin, kung anong gagawin niya, no? So, first, saan na ba yun? To. So, status word muna. Okay, mag-send yung transmitter natin. Anong status mo? TBMT. Okay? Once sa TBMT, papasok na yung wala nang laman yung transmit buffer ko, no? Okay, so papasok na yung parallel input data sa CPU. Okay? Ay sa UART natin dito sa transmit buffer register. So papasok dyan with syempre yung active condition natin sa TDS. Okay? Then lilipat na yan sa transmit buffer register. Okay? And then ang mangyari class is yung control word register, since sinabi niya na lahat ng gagawin, so pagbaba ng transmit buffer register dito, syempre dadaan din dito yung data natin sa data parity and stop bit steering logic. Okay, then Pagkalagay na sa transmit shift register, andyan na lahat ng details. So, yung parity, kung ilang start and stop bit, okay? RCP, mga ganyan, no? Then, i-output na yan, class, sa output circuit. Then, syempre, meron tayong transmit clock pulse dyan. Okay? Then, pagkalabas sa transmit serial output, okay? Pupunta na sa TEOC to. Okay? Ano yung TEOC? TEOC is transmit, ano na nga ba yun? Transmit end of the character. Means na, tawag dito, na-transmit ko na lahat yung buong character. Okay? And then, siyempre, pag na-transmit na, ma-empty na yung transmit shift register, then transmit shift register empty logic circuit. So, bababa na yan. So, wala na namang laman. Okay? Then, SWE, transmit status word, empty na naman siya. Then, same process. Okay? So, tanong ko muna yung status. Kung hindi pa empty, hintay mo muna. Okay? So, tanong ng tanong yung CPU kapag may gusto siyang i-transmit. SWE, hanggang ma-receive niya yung TBNT. Then, saka na mag-go yung process. Okay? Next, we have a UART receiver. So, a simplified block diagram of UART receiver is shown in the figure. The number of start and stop bits and data bits and parity bit parameters specified for the UART receiver must be the same as those of the UART. So, yung control word, dapat parehas sila, no? The UART receiver ignores the reception of idle 1 lines. When the valid start bit is detected by the start bit verification circuit, okay, ito, ito, start bit talaga to, sabi niya, no? Doon na makakapasok yung data class, no? Okay, so start bit, when valid start bit is detected by the start bit verification circuit, data character is clocked into the receiver shift register. If parity is used, the parity bit is checked and in the parity checker. Anong gagawin nun? Malamang, i-check na kung may mali or wala, no? After one complete data character is loaded into shift register, the character is transferred to the in parallel. The character is transferred in parallel into the receive buffer register. So, shift register muna. Then, kapag okay na, pupunta na tayo sa receive buffer register. So, the receive data available flag is set in the status word register. Okay, so magtatanong muna yung yung central processing unit natin. Sabihin niya, anong status mo ngayon? RDA. Ibig sabihin, meron akong data dito na kailangan mong i-receive. Okay? Once na nangyari yun, talon ka na kagad ng 7 dyan. Okay? Sasabihin ng CPU mo, since sinabi ng UART, meron akong data na kailangan mo i-receive. Sabi ng Central Processing Unit, okay, receive data enable means na pwede siyang mag-receive ng data. Ano number 8? Malamang, yan na yung, since sinabi ng CPU natin na pwede na siyang mag-receive, ang gagawin ng UART, ipapasa niya na yung data. Okay, parallel data. Then, number 9, sabihin ng Central Processing Unit natin na receive data available reset. Okay, means na tawag dito, kailangan mo nang i-reset yung yung register mo. Anong UART. Okay? Para makapag-receive siya ng bago. Okay. Ano naman yung 5, 6 at saka yung, tama, 5 and 6, no? Yung kapag nag-status word enable ka, then kapag may error. Pag sinabi ng CPU na RAPE, RFE, kung ano. Okay? Diretso ka na agad sa 9. Receive data available, reset na agad. Kasi hindi mo na kailangan i-receive yun. Okay? Once na may error. Okay? So, ito na. Muna natin. So, CPU reads the status register by activating the status word enable signal, and if RDA is received, the CPU reads the character from the receive buffer register by placing an active signal on receive data enable. O, diba? Nag-jump ka agad ng 7, no? After reading the data, the CPU places an active signal on the receive data available reset, which resets the RDA pin. Meanwhile, the next character is received and clocked into the received shift register, and process repeats until data has been received. So figure shows the received signaling sequence that occurs between CPU and UART. So with synchronous data transmission, precise timing is less important than following an agreed-on format or pattern for data. Each transmitted data character must be preceded by a start bit and end with one or more stop bits. So because data received by UART have been transmitted from a distant UART whose clock is asynchronous to the received UART, bit synchronization is achieved by establishing a timing reference at the center of each start bit. Therefore, it is imperative that a UART detected the occurrence of a valid start bit early in a bit cell and establish a timing reference before it begins to accept data. Okay, wait lang class. So the primary function of start bit verification circuit is to detect valid start bits, which indicate the beginning of a data character. So figure shows an example of how a noise can be misinterpreted as a start bit. So the input data consists of continuous strings of idle ones, which are typically transmitted when there is no information. Idle line ones are interpreted by a receiver as continuous stop bits. Okay? If a noise impulse occurs that causes the received data to go low, di ba? Meron tayong high to low transition. At the same time, the received clock is active. The receiver will interpret the noise pulse as start bit. Wala naman talagang sinesend na data. So if this happens, the receiver will misinterpret the logic condition present during the next clock as the first data bit. So, and the following clock cycles as the remaining data bits B1 to B2 and so on. The likelihood of misinterpreting noise hits as start bits can be reduced substantially by clocking the UART receiver at a rate higher than the incoming data. So figure shows the same situation as shown in the previous figure, except the received clock pulse is 16 times higher than the received serial data input. So once a low is detected, the UART waits 7 clock cycles before resampling the input data. Diba? So meron tayong first pulse. Okay, meron tayong first pulse. Bakit 7, no? Kasi 'di ba 16 pulses yan, 16 times yan eh, no? So, sa half lang. Half lang nung period natin. Okay? So, yung una may na-detect na to kasi leading edge eh. Dito yung leading edge niya 1 pa rin. Pagkadating dito, yung leading edge nung pulse na to, ang na-detect niya class is low. Okay, pero wait lang. Kailangan ko munang maglaan ng 7 pulses na additional bago ko interpret to as valid start bit. So, bilang siya ng 7. Nung nasa 7 siya, niresample niya. Bumalik sa 1. Ibig sabihin, noise lang yun. Okay? Okay, so, syempre, kung na-detect niya class na low yung nung nag-resampling siya, low pa rin, so it assumes that a valid start bit has been detected. If the data have reverted to the high condition, it is assumed that the high to low transition was simply a noise pulse and therefore ignored. It is ignored. Once a valid start bit has been detected and verified, the start bit verification circuit simply samples the incoming data once every 16 cycles. Okay, once every 16 cycles. Diba, na-detect na to. Maghintay siya ng 7 pulses. Pag na-confirm na low pa rin siya, so magbibilang siya ng 16 pulses. Then kung ano man yung masample niya dun, 0 or 1, yun na yung first bit or bit 0. And so on. Every 16 pulse siya mag-re-resample. So the UART continues sampling. Ay, sorry. Sana ba tayo? Tama. The UART continues sampling the data once every 16 cycles until the stop bit is detected or are detected, at which the start bit verification circuit begins searching for another valid start bit. So the UART are generally programmed for received clock rates of 16, 32, and 64 times the received data rate. Another advantage of clocking a UART receiver at a rate higher than the actual received data is to ensure that a high to low transition is detected as soon as possible. So yeah, this ensures that once the start bit is detected, subsequently samples will occur very near the center of each data bit. A difference in time between the sample is taken and the actual center of the data bit is called sampling error. So, nagkakaroon pa rin tayo ng sampling error dito, class. So, yun. Ito yung gitna nung nung start bit. Pero dito yung pang set, di ba? 0 pulse to, pang 0. So, 1 to 7. So, yung 7 pulse dito. Okay? Kasi mag-wait ka ng 7 additional. So, yung 7 pulse, may pagitan siya central ng start bit or center of start bit. Eh, doon dapat talaga yung reading. Okay? Pero hindi mo ma-perfect yung class. No? So, meron talagang sampling error. Yan. Okay? Yung difference ng kung saan nag-sample yung pang 7 na bit, then yung center ng start bit. As figure shows, the start bit is not immediately detected. The difference in time between beginning of the start bit and when it is detected is called detection error. So the maximum detection error is equal to the time of one received clock cycle. So if the received clock rate and a value equal the received data rate, the maximum detection error would approach the time of one bit, which would mean that the start bit would not be detected until the end of the bit time. Obviously, the higher the clock, the higher the received clock rate, earlier start bit would be detected. So, kapag dinagdagan pa natin yung number of pulses, mas ma-detect kaagad yung start bit. Because of detection error, successive samples occur slightly off the center of the data bit. It would not present a problem with synchronous clocks as the sampling error would remain constant from one sample to the next. However, with the synchronous clocks, the magnitude of sampling error of each successive sample would increase, eventually causing a data bit to be either sampled twice or sampled at all, or not sampled at all, depending on whether the received clock is higher or lower than transmit clock. Okay, so let's continue. No? So, figure illustrates how sampling at higher reduces the sampling error. So, first figure shows the data sample at rate 8 times the data rate and 6 and 16 times the data rate respectively. So it can be seen that increasing sample rate moves the sampling time closer to the center of the data bit, thus decreasing sampling error. So placing stop bits at the end of each data character also helps reduce the clock slippage, sometimes called clock skew, problem inherent when using asynchronous transmit and receive clocks. Start and stop bits force a high to low transition at the beginning of each character, which essentially allows the receiver to resynchronize to the start bit at the beginning of each data character. Kasi ito class, di ba? Per character siya kapag asynchronous. So it should probably be mentioned that with UARTs, the data rates do not have the same in each direction of propagation. However, the rate at which data leave a transmitter must be the same as the rate at which the data enter at the receiver at the other end of the circuit. Yung papasok dun sa receiver, dapat the same. If you transmit 1 to bps, it must be received at the other end at 1 to bps pa rin. Then, USRTs. The USRTs is used for synchronous transmission naman of data between DTE and DCE. So, synchronous data transmission means a synchronous data format is used and clocking information is generally transferred between the DTE and DCE. And USRT performs the basic functions as a UART except for synchronous data. So the primary function of USRT are the following. So same lang siya. So we have serial to parallel and parallel to serial conversion. We have error detection by inserting parity bits in the transmitter and checking parity bits in the receiver. Then we have insert and detect unique data synchronization characters, yung sync character. Yan pa rin yan, no? So yan yung napalitan na kasi sa UART, it is adding of and removing of start and stop bits. Next, formatting data in transmit and receiver through 3 and 1 to 3. Example, combining items 1 to 3 in a meaningful sequence. Then provide, transmit, and receive status information in the CPU. Voltage level conversion between the DTE and serial interface and vice versa. And provide the means of achieving bit and character synchronization. Okay. So, yung next na natin serial interface, which we will be tackling next video presentation. So, if you have any questions, class, feel free to ask. Maya, send me your questions in our GC or tawag dito, PM. No problem yan. No? So, okay naman nata. Okay, so next na to, serial interfaces. So, before we end this session, let us pray in the name of the Father, of the Son, and of the Holy Spirit. Amen. Lord, thank you for this day you given to us. Thank you for the opportunity to conduct this video lecture. May you help my students watch this and guide and bless us always. Give us and our families the healing and protection we need against any sickness, Lord, especially COVID-19. This we ask in Jesus' mighty name. Amen. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. So thank you class for listening and see you on our next video presentation or even telecon class.